In this video, we're going to discuss the concept of implicit differentiation. So we will start with this example. Find the derivative of y with respect to x. So dy dx for y minus 2x equals e to the 3x plus 1. So when I look at this, find the derivative of y with respect to x. This lets me know that I can say y is a function of x. And so dy dx is the same thing as saying y prime or f prime of x. So these are the same things. So here I have y minus 2x equals e to the 3x plus 1. So one of the things that I would probably do is solve for y, right? When you see find dy dx, it's like, oh, well, I want to get y by itself on one side. So solve for y, so add 2x to both sides. So I'm going to have y equals 2x plus e to the 3x plus 1. And so now this looks like y as a function of x, and so I can take the derivative. So when I take the derivative, I get dy dx equals, and I take the derivative of this side, everything with respect to x, right? So essentially what I did is I'm taking the derivative with respect to x of both sides. And so here I get dy dx. On the other side, these are already functions of x, so I just take the derivative using my rules. So the derivative of 2x is just 2. The derivative of 3 to the e to the 3x is e to the 3x, right? We always get the exponential back times the derivative of the exponent. So times 3, and the derivative of a constant by itself is 0. So I will have my dy dx, then it's just 2 plus 3 e to the 3x. And that will be our derivative. Now another way I could have done it is I don't have to solve for y. So what do I mean by I don't have to solve for y? So I could have said, well, here's my function, and what I want to do is find the derivative of y with respect to x. And so then I can say, well, I can do the same thing that I did above. I'm going to take the derivative with respect to x of both sides of this equation, right? So then on the left side, I'm going to have the derivative of y with respect to x, which is just dy dx, minus the derivative with respect to x of 2x equals then the derivative with respect to x of all of these. And so here I just get dy dx minus the derivative of 2x with respect to x is just 2, and then 3e to the 3x plus 0. And now in this case, now I'm solving for dy dx. And so that means add the 2 to both sides. So I'm going to have dy dx is equal to positive 2 plus 3e to the 3x. Do we get the same thing? Yes, right? So what's the difference? Well, here I solved for y, and then I found a derivative. Whereas here I didn't put the y in terms of x. I just know that y is a function of x, so I can just take the derivative with respect to x of both sides, and notice that I still get the same thing, right? So one, I solve. So this is why we say is explicitly a function of x. So in this case, let me write it down below. So when I solve for y, so when we solve for y, and just to be able to say y equals f of x, right? So in our example, we had y equals 2x plus e to the 3x plus 1. Then this is, we say y is explicitly a function of x. So I can see that y equals something with an x in it, so I can then say y equals f of x, right? Y is a function of x. When I leave it as it was, when I don't solve for y, then we just have the original function y minus 2x equals, or the original curve, e to the 3x plus 1. So here I don't solve for y, but because I say I want to find dy dx, then here we say that y is implicitly a function of x. So meaning it is implied that y is a function of x, but I don't write it as y equals f of x. So then we say y is implicitly a function of x. We understand that the value of y depends on the value of x, but we're not solving for y to write it as y equals f of x. So I hope that that makes sense. So let's try another example. Or I should say examples. So for example, if I say explicitly functions of x, I will say things like y equals mx plus b, right? So the general equation of a line, or if I tell you y equals e to the x plus sine x minus 2, or y equals x squared plus 1 over secant x minus 7. These are these are functions of x, right? All of these are y equals f of x. Now, when I talk about implicit functions, it will be when I don't solve for y. So I will have something like xy plus 2 equals x minus 7. Right, so I don't solve for y. Or I could have sine of xy equals e to the x plus y. So this will be saying that y is a function of x, but I'm not saying y equals f of x. And so I could have like y times cosine of x equals e to the x minus xy. So all of these will be saying y is implicitly a function of x, meaning y depends on the value of x, but I'm not writing y equals f of x, right? So I'm not saying y is explicitly a function of x. Maybe I shouldn't say not equals, but I don't write it as y equals f of x. So we don't solve for x. So we don't write y as a function of x. So that's what it means to be implicit. And now that I showed you these implicit functions, that's where implicit differentiation is going to come in. Because here, when I write y explicitly as a function of x, right, where I solve for y, notice that I can take the derivative of these pretty standard. Y equals mx plus b, the derivative will be m. The derivative of y here, I just take the derivative of each of this. For the third one, I will use the quotient rule. But here, when things are implicitly functions of x, so I know y depends on x, but how do I find dy dx for these functions? Right? Especially notice the second and the third. I can't really solve for y. And so how do I still find the rate of change? As x changes, how does y change? So that's where implicit differentiation comes in. So let's try an example where we will do it both ways. I will find the derivative here explicitly, and we will also do it implicitly. And then you'll when we do it implicitly, you'll appreciate the implicit differentiation aspect of it. Since we want to find the equation of the tangent line, so task is finding the equation of a line, so I should be ready to put everything into our point slope form. And in this case, we have the point is 3, 4, so I can say y minus 4 equals m x minus the x value, which is 3. So we really just need the slope. And we know that the slope is f prime of x, or with the other notation, dy dx, or you can also call that y prime. And so how do we find dy dx? We'll do it two ways, right? Finding it explicitly, so meaning solving for y in terms of x, and then we'll do it implicitly when we leave it, we don't solve for y. So let's try the first method. let's write y equals f of x, meaning solve for y. So what we have is that x squared plus y squared is equal to 25. Solve for y, so subtract x squared from both sides. So we're going to have 25 minus x squared, and then take the square root. So I'm going to have y equals, anytime you take the square root, you get plus or minus. So I'm going to have the square root of 25 minus x squared. Now here, because I am looking at where the point is at the 0.34, the y value, notice that the y value is positive here. So that means that I am looking at the top of the circle. When you graph a circle, so let's pretend that this one is of radius 5. So you're going to have x equals 5 here, negative 5, and then 0. So when you're looking at the 0.34, that is over here. So I'm looking at the top half of the circle. And because of symmetry, there's also another point over here, right? The 0.3, negative 4. But this is the 0.34, so I'm looking at the top half of the circle. So because I'm going to say, since using the 0.34 is our point, then that means y is going to be the positive square root of 25 minus x squared. So these are some things to take into consideration when you are trying to write y as a function of x explicitly. So this is our function, and now I can find the derivative. So dy dx then will be the derivative of this side, which is 25 minus x squared to the 1/2. And now, good thing that we know about the chain rule, because I need the chain rule here. Notice I have not just x to the 1/2, I have to the 1/2, I have stuff to the 1/2. So the derivative of this will be 1/2 the stuff left alone inside to the negative 1/2, and then by the chain rule times the derivative of the inside. So let me say that this is by the chain rule. And so let's take that derivative. So I'm going to have dy dx is equal to 1/2 25 minus x squared to the negative 1/2 times the derivative of 25 minus x squared, which will be minus 2x. So simplifying this derivative, dy dx is, let's see, what's going to be in the denominator. I'm going to have this 2, and I have a negative exponent, so this is going to be 2 and to the negative 1/2, right? So 25 minus x squared to the positive 1/2, and in the numerator I'm going to have that 1 times negative 2x. And so we can reduce. The 2 divided by 2 is 1, so we're left with just negative x in the numerator. So dy dx is negative x over the square root of 25 minus x squared. So this is our dy dx, right? This is our derivative, which means the formula for finding slope at any point. Where do we have to find the slope? When x was 3. That was the task. Find the equation of the line at the 0.34. And notice that now with this graph here, it makes sense then that the slope is negative. We have a negative x there because the tangent line is going to be right there, which has a negative slope. So what is the slope? Plug in 3 in here and we'll have our slope. So dy dx is negative 3 over the square root of 25 minus 3 squared, which is 9. So negative 3/4 is our slope, right? 25 minus 9 is 16. Square root of 16 is 4. So that's our slope. So now we can finish the equation of our line. So therefore the line, the tangent line, will be y minus y1, which was 4, equals m, which is found the slope to be negative 3/4 times x minus 3. And so this is the equation of our tangent line. So that was using method 1, where we write the function explicitly. We write y explicitly as a function of x. Now the method 2 is we don't solve for y. Alright, so we do not solve for y, but we know that y is a function of x. So we want to find dy dx. So I know x squared plus y squared equals 25 is my function. So how do I take the derivative with respect to x if I don't solve for y? So that means we're going to take the derivative with respect to x of both sides. Right? So that means that I'm going to have the derivative with respect to x of x squared plus the derivative with respect to x of y squared equals the derivative with respect to x of 25. Two of these, I hope you're able to see that they are simple. The derivative with respect to x of x squared, that's 2x. The derivative with respect to x of 25 is 0. That's just a constant. What about this, the derivative with respect to x of y squared? Now notice that I did say here that y, we know that y is a function of x. So let me ask you this, if I take the derivative of y, what is it? So y prime is, take the derivative of both sides, right? So that's f prime of x. So now let me ask you this. This is a little tangent here, but if I had f of x square and I want to take the derivative, how would you take the derivative of that? So if I wanted to do the derivative with respect to x of f of x quantity square, what would you do? By chain rule, this will be 2 times f of x, right? Then times f prime of x. Yeah? You with me? Using the chain rule, right? Think of if that was cosine x squared, you will do 2 cosine x times the derivative of cosine x. If this was something else, like even just x, right, then this will be x squared. The derivative will be 2x times the derivative of x itself, which will just be 1. So going back to the fact that this is equal to y. So according to this, what is the derivative then? Right, then this will be 2 f of x is equal to y, so this will be 2y times the derivative of y times dy dx. I know this is a little different. Let me try to keep those as brackets to be consistent there. So I have 2y times dy dx. So that's what's going to go in here. So then this is really 2x plus the derivative of y squared is 2y times dy dx because of the chain rule equals 0. So I'll let you process that. Pause the video if you need to and take a look at what I have in this little box here to the side. Does that make sense? Just to review, right, since we're saying that y is equal to f of x because y is implicitly a function of x. So I'm not solving for y to have it explicitly in terms of x, but I know that the value of y depends on the value of x. So that's where the implicit comes in. So implicitly, y is a function of x, meaning the value of y depends on the value of x. So when I take the derivative of y, y prime is really f prime. So when I have f of x squared, right, which is my y squared that I have there, the derivative of this by the chain rule is the outside being the square, so 2 f of x to the 1 times by the chain rule the derivative of the inside, so f prime of x. So replacing our f of x with y, this is what we get, right? The derivative of y squared with respect to x then is 2 times y times dy dx. So this is really, really huge. And now we solve for dy dx. So subtract the 2x. So I'm going to have 2y times dy dx is equal to negative 2x, and then get dy dx by itself, so divide both sides by 2y. Why dividing? Because these are being multiplied. So my 2y's cancel, and I'm left with dy dx, which is what we want, our derivative, equals to negative, the 2's will cancel here, negative x over y. And for implicit, then I really need the full point, right? I need both the x and the y. So at the 0.34, what's the derivative? Dy dx is negative 3/4, which notice is the same thing that we got before. So here's our derivative before. Dy dx was negative 3/4. And so here we still get dy dx is negative 3/4. But look at the derivatives. It is so much nicer to do it implicitly than to the method 1, right? Solving for y, and then here having to decide which one do I want. When I take the square root of something, we get plus or minus. So which is the part that I need? So I need to look at my point. Oh, I need the top half of the circle, so I only need the plus. And then do chain rule here and get this kind of ugly looking derivative, and then plug in the value and we get our derivative. With implicit, because I don't have to solve for y, that work is gone. I still need the chain rule, because when I take the derivative of y is implicitly a function of x. So I'm always going to need chain rule when I take the derivative of y. And so it's going to, in this case, 2y dy dx. But notice that we get the same slope. So our equation of the line will be exactly the same. Let's practice some quick implicit derivatives so that you get an idea of what this taking the derivative of y implicitly means. All right, let's try these two quick examples. So find dy dx for these two. Now for the first one, finding dy dx means taking the derivative with respect to x of both sides. So I'm going to do ddx of the left and ddx of the right, taking the derivative with respect to x of both sides. So that means on the left, the derivative of x with respect to x is just 1. And you can see here dx over dx is 1. So I just get 1 there. The derivative with respect to x of sine of y. Now here I have sine of, so always think of this whenever you see the y, picture it as an f of x. So this is really sine of f of x, right? So how do you take the derivative of something like that? You need chain rule, because it's not just x inside. So here we need the chain rule. So the derivative of sine of y then will be the derivative of sine is cosine of the inside left alone, so cosine of y left alone times the derivative of the inside. What's the derivative of y with respect to x? The derivative of y with respect to x is just dy dx. And so that will be our derivative. So I have 1 equals cosine of y times dy dx. If I wanted to solve for dy dx, divide both sides by cosine of y. So I'll have 1 over cosine y equals dy dx. But what's 1 over cosine? Secant. So I have secant of y will be my final answer for dy dx. Now for the second one, notice that this one is a little more interesting. The first one, you could still solve for y, right? Do sine inverse of both sides, and you could still write y explicitly as a function of x. But for the second one, you really can't solve for y, because if you try to isolate y, you're going to have e to the y minus y on one side equals x, or 1 minus x. But there's no way then to get y all by itself when one y is stuck as an exponent and the other one is a base of a polynomial, right? A linear function in that case. So there's no way really that we could write y equals, we can't solve for y. So we have to, in order to find the derivative, we have to use implicit differentiation. So finding dy dx, take the derivative of both sides. So I'm going to have ddx of the left side is x plus e to the y equals, and I'm going to take the derivative with respect to x also of the right side. And so what's the derivative? So here I'm taking, and I'm going to do some extra steps here. So the derivative right of the sum is the sum of the derivatives using that property of derivatives. So dx, the derivative with respect to x, that's just going to be 1, plus the derivative with respect to x of e to the y equals the derivative with respect to x of y plus the derivative with respect to x of just 1. You don't have to do this step. I'm just trying to be very intentional in what I'm taking the derivative of with respect to what variable. So the derivative of x with respect to x, dx over dx, that's just 1, plus the derivative e to the y. Now, again, think of this as e to the f of x. And so know that then here you need chain rule. Chain rule, anytime you're taking essentially the derivative with respect to anything with the y, with respect to the variable x, you're going to need a chain rule. So then this becomes the derivative e to the stuff. The derivative e to the stuff is e to the stuff. So I'll get my e to the y back times the derivative of the stuff. So the derivative of y with respect to x equals the derivative of y with respect to x, and the derivative of a constant with respect to any variable, that's just 0. And now notice that here, to solve for dy dx, I need them on the same side. So I'm going to subtract the e to the y dy dx. So I'm going to have 1 equals dy dx, the original dy dx on the right, minus e to the y times dy dx. And now you can factor out the dy dx. Right, factoring, I have two terms. When I factor out a common factor, being the dy dx here, I should still have two terms inside. And now divide by 1 minus e to the y. So if I had something here like find the equation of the line tangent to this curve at a particular point, I would really only need the y value here, but I still need both values. So with the implicit differentiation, you should always get both values, the x and the y coordinate for the point, if you're trying to find the equation of a tangent line. In the next video, I'll continue with an example of how does implicit differentiation work in real life applications, and then we'll continue with more and more examples, because then how do you use product rule, quotient rule, and continuing to use the chain rule with implicit differentiation. All right, so let's go on to part 2 of the implicit differentiation video series.